A variable inductance, L, is realized by this circuit that is designed using 5 ideal op-amps, a 2 capacitor C1, C2, and a potentiometer KR. K is the parameter. And interestingly, we can see that we can prove that the value of inductance realized is depending on the parameter K and the value of C1, C2 R square. And interestingly, with the proper selection of the capacitors and K, then we have a chance at realizing both positive and negative inductance in this circuit. Okay, so let's apply the test voltage. So similar to all practices before, I am going to apply a test voltage here, V test or Vin, and then try to find the current I, so that then by finding Zin equal to V over I, we can find the input impedance and prove that it is actually an inductance realized while not having any inductor in this circuit. Okay, so the voltage V is applied. Of course, V appears here. We assume that all the 5 op-amps are properly biased and with the positive-negative supply voltages connected. And we make the assumption that negative feedback as shown here is dominant compared to positive feedback for both op-amps, all op-amps here, and therefore circuit is stable in linear region of operation, not saturated. Because of that, virtual short is valid. So virtual short is valid, which means the voltage at the negative terminal of each op-amp equal to voltage at the positive input terminal for that op-amp. So now the voltage is V here, therefore voltage V is here. As a result, it's also here, which means it is here. As a result, it is here, and therefore it is also here. The same argument that voltage V is here. For the same reason, virtual short, it is here as well, it is here, and finally it is here. Okay, so that makes life much easier, because we can find this current, which is equal to, let me put it here, so that current is equal to V equal the current. Let's say the current Ix is equal to V over R. That current cannot go through the input terminal of ideal op-amp because it has infinite impedance. So that current should come this way. Okay, so that's the good news. We can say the voltage is here, and there is this current flowing, so we can find the voltage drop across this resistor. And that should be the voltage drop across this resistor, because both of these two resistors have the same voltage across them. On one side, they both have V. On the other side, they have a common node. So we can find this current, let's say IY, this way. I can say VR equal to VR. Basically, I'm trying to say that the voltage drop across these two resistors is the same. So that means RIX should be equal to RIY. As a result, IY with the direction that is shown there is equal to IX. So great, IY with this direction is equal to V over R. Okay, so nothing can go through the positive terminal of ideal op-amp as long as it is not saturated, so that current IY is flowing to C2. For the same reason, the voltage drop across C2 is the same voltage drop across R. So I can find let's say the current IZ, and I can say IZ equal to, let's put it this way, the voltage across that resistor R should be equal to voltage across cap C2. And we are doing S-domain analysis, so I can say RIZ equal to 1 over C2S, which is the impedance of cap, times the IY. So with the direction that is shown here exactly, I can say IZ is equal to 1 over R C2S IY. So let's keep that. Now, the same reasoning, no current can go through the terminal of ideal op-amp, input terminal, so that's IZ has to go this way. So that's IZ. And for the same reason, the voltage drop across this resistor R is the same voltage drop across this KR, because they have common voltage nodes on for both of them on both sides of resistor. So if there is this current IW, then I can say voltage across KR should be equal to voltage across R, which means KR IW equal to R I2, IZ, and therefore as a result I can say IW equal to IZ divided by K. Okay, great. So let's name this 1, let's name this 2. As a result, I can combine these two, and I can say, so from 1 and 2, and actually let's name, we all know that Iy equal to Ix, so that's also 3, and we know that Ix equal to V over R, that's 4. So from 1, 2, 3, 4, I'm getting this outcome that IW is 1 over K, substituting for IZ here, 1 over R C2S, then substituting for Iy, Ix, but then substituting Ix V over R, so V over R. Therefore, conclusion, IW is 1 over K R squared C2 S V. So let's keep this as equation 5. Now, one interesting outcome, be careful that the thing we found here, let me use, just for this one, let me use a different color because I need to do so. Direction of, the direction of current IW in this conversation, given what I showed you, is this way. So it's effectively a negative current because as we apply voltage V, we expect current I going inward, but this current IW is coming out of the circuit, so it's like a negative current if you think of it as this direction rather than the actual direction we found. Okay, for the same reasoning, if I name the current that is going downward this way on the lower branch as current I, let's say, let's have a name for it. This time, let's say it's the current I coming with a name. Let's say IC, for example. That's confusing. Let's say ID. That's fine. So for that current ID, then I can say, for that current ID, I can say the same reasoning. So it's going to be with this direction. For the same reasoning, using the same mechanism, using the same, let's say, logic and thought process as I showed you for IW, I can say that ID with the direction that is shown there is equal to V over K, not K, there is no K there, R squared C1S. That's the equation number 6. Now, using 5 and 6, what I can say is the total I is, with the direction that is shown, is ID, that is going outward similar to I, minus IW, because IW is actually coming back from circuit like a negative current. So minus IW is equal to, now substituting from 5 and 6, is equal to V over R squared C1S minus V over K R squared C2S. Let's factor out V over R squared S. What remains is 1 over C1 minus 1 over K C2. Great. Okay, so what I learned is I can simplify this. V over R squared S, and then KC2 minus C1 divided by KC1 C2 divided by KC1 C2, and we are done. Because what this is, as we found, this is I. So I found I, and we know that as a result, let me put it here, input impedance is simply V over I, as we talked about it at the beginning of this conversation. So V squared is Z in is V over I, and then using what we found here, it simply means Z in is exactly what at the beginning we said it's going to happen. So Zin is Kc1 is Kc1 C2 divided by Kc2 minus C1 times R square S. And as soon as we find this, obviously this resembles Ls as an inductor, in which the value of L is as described at the beginning of the problem, Kc2 C1 divided by Kc2 minus C1. Now interestingly, if we set C1 equal to C2, then L, which is realized in this circuit, becomes as simple as K over K minus 1 times C R square, which is very interesting. So in that case, we have a programmable inductance that using the potentiometer K, we can adjust it, and actually, depending on what the value of K in the potentiometer is, it can realize a negative inductance or a positive inductance in the circuit, as long as the circuit is in practice stable. I hope that this is helpful.